All right, let's take a look. So, okay, again, I don't want to spend a tremendous amount of time on this because when I show you L'Hopital's rule in the, not too distant future, this will become very, very simple. Okay, but there is a technique here. It's some value in just knowing how to rewrite this in a way where we could get an answer algebraically. Okay, it's just good algebra practice. So if I try to evaluate this directly, what do I get? I don't get 0. I get 0 over 0, right? So it is an indeterminate form, which means I've got to resolve the indeterminacy. I've got to do something. Okay, when we're dealing with a trig limit like this, what is the special limit that we're probably going to use? Yeah, the limit, I'm going to call it theta. Limit of sine theta over theta as theta approaches 0 is what? 1. So that's the special limit that we want to use. Okay, what are we missing here? What does our theta have to be? Has to be 4t cubed, because that's what's trapped inside the sine function. I can't really manipulate the angle inside the sine function easily at all, right? I mean, I can through a combination of half angle formulas and double angle formulas, but you don't want to do that. That's a lot of work. So we're stuck with theta being 4t cubed. It's pretty easy for us to manipulate the theta that ends up on the bottom, right? What do I need to be on the bottom? 4t cubed, right? What do I have there now? Negative 2t. And I could even just do this, right? I mean, the negatives, why don't I just cross those out, right? A negative over negative is positive. So then what do I need to multiply? What do I need to get on the bottom? 4t cubed. I have a 2t. How do I accomplish that? I multiply, say it again. Where? Top and bottom, because I'm really just multiplying by 1, okay? So then this gives me, so this is the limit of, I've got my sine of 4t cubed over, on the bottom I'm going to end up with 4t cubed. To get that, I had to multiply top and bottom by 2t squared, right? And this should be a limit. It's not equal to that. It's equal to the limit of that. So I got to be sure to include the limit notation. Whoops. As t approaches 0. But as t approaches 0, so does 4t cubed, right? Okay, yes? And that's still there. You're right. So that's going to be an 8, isn't it? You're right. I multiplied top and bottom by 2t squared, right? Everybody good? Okay, so now what? Okay, I can't move the 8t squared out in front because it includes a t. And I can only move constants out front. But I could split this up into 2 separate limits because I have a property of limits that's important here, right? The limit, remember, the limit of f of x times g of x as x approaches a is equal to the product of the separate limits. Oh yeah, grab it, absolutely, you betcha. Right, everybody remember that? Important property. So we'll split this up into 2 separate limits. I've got this limit out front. Let's take this piece first. So I get the limit of 8t squared as t approaches 0 times. Now we'll deal with that part. Times the limit of sine of 4t cubed over 4t cubed. But as t approaches 0, so does 4t cubed. Okay, and now I can answer both of those limits. I can directly evaluate and get answers, right? I mean, this one I can't directly evaluate, but it fits my special limit pattern. What's the limit of the red limit? It's 1, exactly. What's the blue limit? What's the blue limit, everybody? 0, yep. Any question? Why does it what? Mm-hmm. Mm-hmm. Well, okay, you decide. Either you can or you can't, because it's one or the other, they're equivalent. A times B over C is exactly equal to A times B over C, isn't it? Right. You could pull that A out in front if you wanted to. That's fine. Yeah, yeah. Okay, makes sense. And so then we get the answer. This is equal to 0 times 1, which is 0. So our answer is 0. Okay, good? Questions? Well, on these trig ones, it kind of is 0 a lot. Yeah. I mean, if you think about that, because if it's a good observation when you're dealing with limits of trig functions using composite trig functions, anytime a numerator in that composite trig function goes to 0, it's going to drive the whole thing to 0, right? So it happens an inordinate amount of the time when we're doing these kind of contrived limit problems like this. Yeah. Mm-hmm. For t cubed. Okay, here's why. Because as t approaches 0, 4t cubed approaches 0. So you can do that for free. It is. And the only reason we do it is just so we match that pattern. Okay? Just so we match that pattern. And it probably, honestly, would even be acceptable to just have that be a t, and you could still say, even if we had just said as t goes to 0, that still implies that that equals 1. Yeah, either way really would be fine. Yeah. Again, this is probably overkill because in like 2 months, within 2 months, you'll have a really quick way to do this problem with no algebra, just doing a little bit of simple calculus. Okay. All right, so here's, I'm gonna give you little tidbits of this. Okay, so today we're gonna start looking, and we'll continue. You guys might need a little time to work. I get that, so I'll give you a little time built in tomorrow. We'll come back to this Wednesday. Infinite limits. Now, infinite limits is confusing in calculus because we're soon going to talk about limits at infinity, which means as x approaches positive infinity or x approaches negative infinity. That's different than infinite limits. We'd call that a limit at infinity. Infinite limits is what happens when a function explodes and you get a limit that's either positive infinity or negative infinity. That's what we mean by that. And that's strongly related to vertical asymptotes. Big surprise, right? If a function is exploding vertically, that creates a vertical asymptote. What are the characteristics of a vertical asymptote? Before we go any further. If you had to tell somebody, what would you expect when you encounter a vertical asymptote? Somebody in a lesser math class, what would you tell them they should expect to see when they encounter a vertical asymptote in a function? The function's getting increasingly vertical, right? Can a function ever cross a vertical asymptote? It cannot. Can't cross. So a vertical asymptote acts like it separates the space of the function into like separate little universes. They're just completely walled off from each other by that infinite vertical wall, right? You can't cross it. Okay, we'll get back to that idea later. So let's remind ourselves, we defined two types of one-sided limits. Before roundup, we were talking about what's it mean if we say the limit of a function as x approaches a with a minus superscript. From the left, from the direction of negative infinity. So it's a limit from the left. And if I have the plus, that's a limit from the right. And for us to have a regular two-sided limit, that can only exist if the two one-sided limits exist and agree. If the limit from the left is equal to the limit from the right, then you have a two-sided limit, right? That make sense? Okay. So in other words, we talked about this, like a couple weeks ago, we talked about this as ants approaching that value from the left and the right would have to anticipate stepping on the same place, meaning their one-sided limits would agree. Okay? All right, so let's look at some interesting functions. This is, when you see something like this is called the greatest integer function. Okay, what does that mean? It outputs the greatest integer that's less than or equal to the input. So what would the greatest integer output be if I input 3.7? 3. What if I input negative 0.1? Be negative 1, right? Because the greatest integer, 0 is not less than negative 0.1, right? The greatest integer that's less than negative 0.1 would be negative 1. Here's how you can kind of think about that. Imagine on the number line you have knots tied at each, tied into the string. It represents the number line at each integer. If I want to input a number value, it's like I'm placing a bead on the string at that point, and I'm just going to shove it to the left as far as it'll go until it hits a knot and gets stuck, right? That's a way to kind of think, just a visual model of that. So if I wanted to graph this thing then, does everybody see that that's what it's going to look like, an infinite staircase? Because if I input a value, like let's say I input a value greater than, 0 or greater than 0, but less than 1. The greatest integer that's less than or equal to 0 is 0. The greatest integer that's less than or equal to 0.99999 is still 0. But the greatest integer that's less than or equal to 1 is 1. So every time we move to another integer, it's going to move us up the infinite staircase one stair, right? And that's what we end up getting. So that's what the greatest integer function looks like. Now, a lot of times now, we don't call it that. A lot of times now, we call it a ceiling function because it's, a floor function, because it's pushing the number down to the floor, meaning we're sliding it down to the next lowest value, next lowest integer. So a lot of times we call that a floor function. Or it'll show up on calculators or on computer algebra systems as INT for greatest integer. So either INTX or floor x. They mean the same thing. Ceiling function would be what then, do you suppose? It's going to, if I input a number, it's going to output what? It's going to output the least integer that's greater than or equal to the input. So like the ceiling of 3.7 would be what? 4. The ceiling of negative 0.1 would be 0, etc. Right? You get the idea? Okay, so there's a function. How come I'm talking about it? Because we're going to use it. So let's try a couple things. If we're going to define the function f of x equals the floor of x divided by x, what's the limit of that function going to be as x approaches 1 from the left? If I evaluate directly, what do I get? What's the floor of 1 minus? So that's the greatest integer function. What would it be? 1 or 0? Vote with your fingers. 0, right? That's the greatest integer function. So if I evaluate, and we say 1 minus, think what we mean. We mean a number slightly less than 1. So 0.99999, something like that. So we're going to get 0. What do we get on the bottom? 1. We're approaching 1 from the left side, but who cares? The number we're approaching is 1, right? So what's 0 divided by 1? There you go. That's the limit from the left. Okay? What's the limit from the right? 1 over, which is 1. Okay? Make sense? So then you tell me, what is the limit of this function as x approaches 1? Yeah. Doesn't exist. Because the two one-sided limits, though they exist, do not agree. So there is no two-sided limit. Okay? Let's try for 0. What's the limit of this function as x approaches 0 minus? Okay, I get negative 1 over 0, which is undefined, right? Well, we could maybe be a little bit more specific. On the bottom, I'm getting 0 minus, aren't I? Okay. So it is undefined, right? It doesn't exist, but I could be a little more specific than that. How? The number on the top is negative 1. Exactly. The number on the bottom is not exactly 0, right? What do you think? For now, let's just say DNE. We'll come back to it. Okay, what about this bottom one? Limit of the function as x approaches 0. What do I get? I get 0 over 0, right? Except, so that seems indeterminate, doesn't it? But I'm telling you that the answer is 0. How come? Yeah, because the number on the bottom isn't really 0, it's 0 plus. It's a number slightly bigger than 0. What's 0 divided by 20? What's 0 divided by 2? What's 0 divided by any non-zero number? Okay, the bottom is a non-zero number, right? Because the bottom is approaching 0. The top is exactly 0. Everybody see that? Interesting, right? So it actually is 0. So what is this going to approach then? Let's do better than DNE. I've got a finite number, negative 1 on the top, and on the bottom I've got a vanishingly small number. So what does that tell you if I have a finite number divided by a vanishingly small number? What's the size of the result going to be? Going to approach infinity, right? Everybody agree? I've got a number on the top that is finite, a number on the bottom that is approaching 0, and so therefore the size of the fraction is going to explode. So you know that the fraction is going to get infinitely big. What's the sign of that infinity going to be? And just all you have to do here is just follow sign conventions. What's the sign of the number on top? Negative. What's the sign of the number on the bottom? It is? 0 minus is slightly less than 0, which makes it negative, right? Okay, what's our sign convention say for negative divided by negative? So it's positive infinity. Okay, so as we approach from the left, we should see positive infinity. As we approach from the right, it should be 0. Let's look at an actual graph of this thing. That's what we get. What do you know? As we approach 0 from the left, the thing shoots up to positive infinity. As we approach from the right, it approaches 0. Okay? So what's the, and this is easy, what's the two-sided limit equal to then? Does not exist, right? Because the two one-sided limits don't agree. One of them doesn't even exist. Okay, make sense? Okay, so we got an infinite result, and so that's why this falls in the section of infinite limits. Let's look at another one. Okay, how about something like this, infinite limits? as x, the limit of the function 3 over 1 minus x as x approaches 1. Well, we know from the very beginning there's three things that can happen when we evaluate limits directly. We get a non-infinite answer, right? We get a finite answer, and we're done. We get an answer where we have a 0 on the bottom but not the top, which means doesn't exist, or we get an indeterminate form like 0 over 0, which means we have to resolve that by doing some more work of some kind. So this one was a does not exist one. Let's be more specific. Let's look at the one-sided limits. So let's take the one-sided limit from the right. As x approaches 1 from the right, what do I get when I evaluate this directly? What's on the top? 3. What's on the bottom? 1 minus 1 plus, right? Okay, well, what is... I think this thing's about to crap out on me, I have a feeling. Let's see. There we go. Okay, do you see that that's what it is? I have 1 minus 1 plus. 1 minus a number slightly bigger than 1. Isn't that a very small negative number? In other words, that's 0 minus, right? Okay, so now, how do we interpret that? On the bottom, we get 0 minus. On the top, we get 3. What's the size of that thing going to end up being? It's going to be infinite, because I've got a finite number on the top and a vanishingly small number on the bottom. So you know you're going to get... Oh, man. Technology. So we get negative infinity. We know we get the infinity because of the blue parts. Finite over vanishingly small. We get the negative infinity because of the sign conventions. Positive number divided by a negative number is negative. Okay, what are we going to get on the when we approach 1 from the left side? We get 3 over what? 0 positive, 0 plus, right? Because we get a small positive number. So what's that going to give me? Yeah, it's going to give me positive infinity, right? It's positive because of, positive because of sign conventions. Right, we just call it infinity. And so what's that tell us about the nature of the two-sided limit? Well, it truly doesn't exist. I mean, it doesn't exist, but we can't see anything more about it than that. It doesn't have consistent infinite behavior from both sides, and so it's divergent, and we can't really say anything about it, about the two-sided limit. It does different stuff from different sides. Okay, compare that to, let's look at this one. Actually, I'm going to scoot up. Let's compare it to, let's look at this guy. We'll backtrack a little bit later. Are we about done?